Okay, this video is chapter 8A from the book about how to prevent dementia. Here's the book, Poor Man's Way to Prevent Dementia and Raise IQ. Okay, we're going to be talking about diabetes today. And the key thing with diabetes, everybody thinks, sugar diabetes, but it's really primarily a fat disease. So there's different ways to describe it. I would call this a conceptual staging system based on the ectopic fat theory of diabetes. I basically just put things in order. We normally accumulate fat, first of all, our subcutaneous areas, a little bit in our visceral areas around our abdominal organs, for example. But it's abnormal for us to accumulate fat in our skeletal muscles. Now, some, like marathon runner or something, might have a little fat there, but for a regular person, they should not be accumulating a significant amount of fat in their skeletal muscles. So, accumulation of fat in the skeletal muscles, I'll call that sometimes intramyocellular lipid, is the first detectable finding with insulin resistance. And the cells will sense something, we're going to call it overnutrition. And what will happen is they will send a signal to the glucose type 4 vesicles to not go up to the plasma membrane. So insulin won't work. Insulin will not be able to send the glucose type 4 transporters up to the plasma membrane in the skeletal muscle cells. And what that'll mean is the glucose can't get into the skeletal muscle cell. Normally after you eat, most of the glucose goes into the skeletal muscle and it's stored as glycogen, which is an energy, polymer of glucose that's used later on when the muscle exercises. Okay, so accumulation of fat in the skeletal muscle is the first detectable finding of insulin resistance. And the consequence is that after you've eaten, to eat is called prandial. So after you've eaten, blood glucose goes up. Okay, so postprandial elevated glucose is postprandial hyperglycemia. Fat eventually starts accumulating more and more in the liver, and then you get fatty liver. And as you get more fat in the liver starts having difficulty correctly regulating blood glucose. The main job of the liver is to make sure your brain gets the right amount of glucose. So it monitors the blood glucose level all the time, and when it starts dropping lower, it releases glucose into the blood. Okay, when you accumulate fat in the liver, it can no longer accurately sense it, and it will release too much glucose into the blood, from breaking down glycogen or from running gluconeogenesis. So glycogen is the storage polymer of glucose. Gluconeogenesis is a pathway by which you can make glucose in the liver, like from amino acids, from proteins, etc. Okay, the next thing that'll happen is you'll start to accumulate fat in the pancreas, and it'll be damaging to the pancreatic beta cells. Those are the cells that make the insulin. And over time, you'll start making less and less insulin, and eventually you might not be able to make a significant amount of insulin at all, and you'll become insulin dependent for the rest of life. So that's insulin dependent diabetes. Typically, diabetes type 1 is young person, autoimmune diabetes, thought most often related to dairy proteins, milk and whatnot, cow milk. Then there's something called diabetes type 1.5, which comes on later, and it's thought to also be autoimmune, but it's not necessarily from dairy. And then the main one we see all the time is type 2, all day long from all the fat middle-aged and older people typically. But nowadays it's occurring even in type 2 is occurring even in teenagers and in young adults. Okay, so once you've got loss of the insulin production from the beta cells of the pancreas, you start getting other complications. First of all, chronic prolonged hyperglycemia is a problem because there's cells in the body which are not like skeletal muscle cells. They don't have an insulin-dependent glucose uptake. They basically are like constitutive, meaning that they just take up glucose based on whatever the blood glucose level. So a transient, elevation in blood glucose, spike, if you will, after eating, that's not a big deal. They'll take a little extra glucose in, but it's not a big deal. However, if that blood glucose is continuously elevated, 24/7, those cells take in too much blood glucose, and it is damaging to them. That includes cells in the retina of the eye, so you get diabetic retinopathy. That includes arterial lining cells, the endothelial cells. They are not glucose insulin dependent, so they just keep on taking glucose up, and they will become overwhelmed by that. So you'll get endotheliopathy, microvasculopathy, you can call it. Some people call it endotheliitis, inflammation of the endothelial cells. Okay, you'll get similar problem in the kidneys. And that will cause, diabetic nephropathy, kidney damage. It causes atherosclerosis all over the body, so it's very common for them to become impotent. Very common for them to have atherosclerotic diabetic microvasculopathy in the small arteries of the foot. And that's a major problem. The foot's a bad spot for vascular disease because when you're standing up, think about it, your blood pressure is highest in your foot because you got a standing column of gravity pushing that blood down. So the higher velocity and pressure of the blood going down to the foot causes more trauma to the endothelial cells. So they're more prone to atherosclerosis. And here's why you're screwed with diabetes in the foot. Because let's say you're a cigarette smoker. They get a lot of aortoiliac disease. It's very easy to get inflow. Inflow is always easy to get. But then you have to bypass, let's say, do a surgical bypass to a target. Or you have to angioplasty or stent. You need a vessel to be a decent size. A couple of millimeters in diameter before you can put a stent in there. And stents don't always stay patent. What I'm trying to say is aortoiliac disease, you got enough diameter there, it's over a centimeter, that vessel, you could bypass it very easily with a surgical graft. You could angioplasty and stent it pretty easily, okay? On the other hand, when you've got a stenosis or occlusion severe down in the foot and you got an ischemic toe that's becoming necrotic, gangrenous, dying, there's nowhere to bypass to. You can't get an angioplasty balloon in some of those little tiny vessels. You can't put a stent in them. They're too small, and you can't surgically bypass because there's nothing to plug into distally. So that's why diabetics get amputated all day long, and every hospital, every Western hospital has a couple of diabetes amputations on schedule for the day. It's super common, unfortunately. Okay, so that's a major complication of diabetes. Then what I would consider like the worst one is, first of all, they tend to die of myocardial heart attacks at a young age. Okay, but then they're notoriously cognitively impaired. I mean, it's pretty routine that, like I said, I got internal medicine friends, and in my own personal experience as well, it's like almost every single patient over 60 is cognitively slow. They're like cows. Yes, thank you. They're very nice, but they're mentally slow. And diabetes really is bad for cognitive function. Okay, here is mitochondria, and this is where the vast majority of energy is made in humans. It has an outer mitochondrial membrane, OMM, an intramembranous space that's between the inner membrane and the outer membrane, so that's called the IMS for intramembranous space. That's where the protons get pumped into, this space right here. And then this green membrane is called the inner mitochondrial membrane, usually abbreviated IMM. And this is where all the electron transport proteins are, and this is also where ATP synthase is. And it is across this membrane that protons are pumped from the center of the mitochondria, called the mitochondrial matrix. They're pumped into the intramembranous space. And then you're going to build up a proton gradient with high concentration of protons in this intramembranous space. And that's like the great secret of life to life on Earth is based on that. Okay, it's saving my document for whatever reason. Okay, let's see, we'll get to my next cycle. Oh, if you want to learn about diabetes, there's good videos. There's good video lectures on it. I've given lots of lectures on this. Dr. McDougall has a good video lecture on this. Those Mastering Diabetes guys got good lectures. I think those guys are good. They're also, eating a low-fat, low-sodium plant-based diet. And McDougall does a good job of letting you know what a big deal all the fat is and how that's been known back since the 1920s. J. Shirley Sweeney took a bunch of medical students. You feed them a high-fat diet, they fail their oral glucose tolerance test. You feed them a high-carbohydrate diet, they do just fine on their oral glucose tolerance test. And that was repeated by a couple of other experimenters like Hemsworth, I think it was Harold Hemsworth, and a guy named Rabinowitz, and Keem, and a whole bunch of them. Everybody got the same results, You feed high fat, you get insulin resistance. In McDougall's words, the fat paralyzes the insulin receptor. That's one way to phrase it. I'm going to phrase it a little bit differently here based on the Brownlee paper, but it's the same thing essentially, Okay, here's glucose, here's palmitate. So glucose is your carbohydrate, and you got a carbon, and it's hydrated. There's, H2O around it. See how that makes sense there? Okay. And that's what it comes out to, a carbohydrated molecule. You got a carbon and a water equivalent around it. Okay, here's a fat molecule. So fat is real dry in comparison. Fat, you just got this long tail of carbons, and then you have a carboxylic acid at the end. That's a fatty acid. you can see that the water is going to be a lot more polar, so it's going to be more soluble in aqueous solution because it's more charged with all those. Oxygen has a much different electronegativity, meaning desire to grab electrons, than does carbon, so it's more charged. Hydrogen and carbon have a similar electronegativity, meaning a similar charge effect that makes them nonpolar. Their bonds are pretty well charged, balanced, if you will, rather than polar with, positive on one side, negative on the other side. Okay, here's glucose normally coming into a cell. Glucose comes into a cell, and then it undergoes a reaction with an enzyme like hexokinase, glucokinase, and they stick a phosphate on it. The phosphate traps it in the cell because it's got a big negative charge on it, and that big negative charge makes it so that it can't get out of the membrane. If you actually care about glycolysis, which you don't really need to know much about it at all, I'm going to give you a little more detail than you need just for the persons who might want to know it. One of the great tricks of memorizing this whole thing, I used to memorize all these pathways, okay, is that it's an aldehyde, okay, meaning that there's just a hydrogen here. Okay, that ends up, if you're interested in memorizing, that'll be a useful trick to know. Okay, then it gets isomerized into fructose. Fructose is a more symmetric molecule, and I color-coded it all the way through because that's going to make it easier to follow the reactions if you actually care about doing that. But the big point to know is this next step here is called phosphofructokinase, where another phosphate is added. And it's it's a perfect name, phosphofructo. You're adding a phosphate to fructose. Kinase is an enzyme that adds a phosphate, and it's abbreviated PFK. So this is real important to know because this step is heavily regulated. So everything that happens with glucose is pretty carefully controlled. Glucose is basically the energy of life. It's the most important food molecule, okay? And then you're going to end up with glyceraldehyde 3-phosphate. Sometimes I'll just call this 3-phosphoglyceraldehyde, 3-PGA. 3-phosphoglyceraldehyde, 3-PGA. And that's a super important intermediate in glycolysis because this enzyme is going to get inhibited when you've got diabetes. And then this is going to undergo side reactions. So 3-PGA gets into all kinds of situations once diabetes gets going. All right, this is just showing you the reactions that follow. And again, you don't really need to know these, but some people might want to have them listed in case they're a little more curious. And when you start looking up all the inhibitors and stuff, having these out here might be helpful to you. But basically, 3-phosphoglyceraldehyde, 3-PGA, undergoes reaction with 3-PGA dehydrogenase. That's the name of the enzyme it reacts with. And you end up with pyruvate, a 3-carbon molecule. It's a carboxylic acid, okay? Then what's going to happen is this is going to be decarboxylated. You'll take off a CO2, and then you'll have just the 2 carbons and an acetyl group, and that'll make acetyl-CoA, and then that will go into Krebs cycle within the mitochondria. Okay, so this picture here, what I'm doing here is I'm giving you the background that you're going to need to be able to understand the more interesting stuff. So again, you've got glyceraldehyde, and like I said, we usually call it 3-PGA. And that normally would go to this next this product, next intermediate in the glycolysis cycle. Oh, things that also inhibit 3-PGA. Well, PARP is a big one. I'll explain to you what PARP means in just a little bit here. It's a DNA repair enzyme that basically goes haywire, bonkers, a disaster in diabetes. Alcohol can also inhibit 3-PGA dehydrogenase. And that makes people stupid. Arsenic is also another inhibitor, and arsenic can be a problem. Arsenic's a lot higher in chicken than it is in rice. Okay. Well, here I was just showing you some of the things that inhibit it. So PARP, that's what we're going to come to in a little while. Alcohol can inhibit, arsenate, related to arsenic. If you got a lot of arsenic on board, it decreases your ability to make ATP. Okay, then you get to pyruvate at the end of glycolysis, and you can Also, if you don't have any oxygen available, you can make it into lactate, so you get a lactic acidosis after, let's say, you're exercising. It can be, in the appropriate context, made into glucose, kind of send it back to glucose in a different pathway in the right time. Like, let's say you have low blood glucose, okay? And normally, though, you're going to send it to acetyl-CoA to run through Krebs cycle. Okay, so what happens then is the glucose, like I said, it comes into the cytoplasm of the cell, hexokinase phosphorylates it, undergoes glycolysis, becomes pyruvate, gets converted into acetyl-CoA, runs through Krebs cycle, sends electron carriers. In a sense, you peel off the electrons. The hydrogen is sent as an electron and a proton, and it goes into the transport proteins on the intermitochondrial membrane, and those are going to pass the electrons along like a fireman bucket brigade. Okay, so here's what normally happens in a mitochondria. The electrons are passed from, this is complex 1, complex 2, complex 3, complex 4, and then ATP synthase, the enzyme is sometimes called complex 5. And the electrons are passed almost like, a ball rolling downhill towards progressively stronger grabbers of electrons. And the ultimate acceptor of electrons is oxygen, under which it is converted into water, H2O. At each of these major complexes, well, complex 1, 3, and 4, a proton, here's a H, is pumped out. H plus stands for a proton, okay? It's like it's a hydrogen with the electron removed. And you're going to accumulate these protons in this intramembranous space between the outer mitochondrial membrane and the inner mitochondrial membrane. And then you're going to harvest the gradient at ATP synthase by allowing a proton to come back into the cell. And the energy of allowing that will spin this ATP synthase, and that'll produce ATP. And that's how energy is made. All multicellular organisms have mitochondria, and that's how they make ATP. That's the main way they make ATP. And it generates an incredible gradient. This is the biggest electrical gradient in the human body that I'm aware of. It's about negative 160 millivolts, meaning that because you're pumping all these protons, positive charges, into the intramembranous space, the charge of the intramembranous space relative to the mitochondrial matrix inside the intermitochondrial membrane is negative 160 millivolts. That's an incredible high charge. If you look at a neuron, which are very electric, they have a membrane charge of like negative 65 or negative 70 millivolts, okay? So this is an incredibly high gradient. This is like your electric, production factory, coal-burning electric plant, okay? And that's what also I think is kind of funny. Humans think they're so smart and the scientists are so smart. This is so far beyond anything humans could do. It's not even funny, okay? Like I said, that's another reason why I believe in God, because I know a lot of biology and chemistry, and it's so amazing. And I don't think it happened by chance. It's way, way, way too complicated. The brain's got 100 billion neurons, and all this complex chemistry is so perfect. I don't think that happened by chance. Okay, let's see, what are we looking at here? Oh, this is just a chart of electronegativities. So as far as electronegativities are concerned, what this means is the strongest electronegativity is F minus, 3.98. The next is oxygen at 3.44. And what that means is electronegativity is desire to grab electrons. And oxygen really, 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 really wants those electrons. So it grabs pretty hard. The only thing that grabs harder is F minus. Okay, one of the things you'll notice in this vertical column here of elements in the periodic table of elements is these are called halogens. And every single one of them is quite toxic to living things. F minus, Cl minus, bromine, iodine. So even though we do use some iodine to make our thyroid hormone, you can also use iodine for surgical prep. I actually like the iodine prep better than the modern chloroprep. But anyways, you need to know that oxygen has a super high electronegativity to grab electrons, and that's what enables it to be the ultimate electron acceptor in electron transport inside mitochondria, and that's why oxygen is essential. Humans can't live without it. Okay, here's just another diagram of how electron transport works. And I'm going over this a lot because you're going to hear about there's tons of medications that mess up the mitochondria, including a lot of famous ones you've heard of, like metformin. Metformin is so overrated. McDougall talks about that a lot, but you'll almost laugh once you learn what it does to the mitochondria. Your statins, they can interfere with coenzyme Q. Okay, great. Because people ask me, I'll have doctors ask me, oh, do you think I should take metformin? I've heard it improves aging. I'm like, yeah, right. A mitochondrial inhibitor is going to improve your aging. Are you stupid? Okay, so here we talked about the hydrogens are split, their electrons are passed down through the electron transport chain. This series of protein complexes in the membrane is called an electron transport chain, electron transfer chain, and it's transferring the electrons, like I said, a fireman bucket brigade, handing them down to progressively more powerful grabbers of electrons, ultimately the ultimate electron acceptor, oxygen. Okay, and then these complexes, as we said here, I'm using red to show the protons being pumped out. And they're pumped out at these sites, 3 sites, and then the gradient is harvested with the proton allowed to come back in, and the energy of that will spin the ATP synthase, and that generates energy that can add a phosphate to ADP, adenosine di, as in 2-phosphate, to adenosine tri, as in 3-phosphate. Okay, and what you're seeing here too, in a sense, this is kind of like miraculous. What has happened is these enzymes have split the atom. You say split the atom, what am I talking about? They've taken a hydrogen and they split it. They pulled off its electron, separated it from its proton, run the protons through this gradient over here, and then run the electron, pass the electrons down this chain. Genius, okay? It's awesome. That's how we make energy, by splitting the atom. Okay, and you make tons of energy that way. You can only make like 2 ATP with glycolysis, but when you run the whole electron transport from 1 molecule of glucose, you can make around 32 to 36. Okay, free radicals in mitochondria. Now what's happening is you need to give 4 electrons to this oxygen in order to convert it into water. Sometimes an electron will leak off of the electron transport chain, and it'll drop down and attach itself to an oxygen, and then this becomes what's called a superoxide. A superoxide is a free radical, meaning that it has an unpaired electron in an outer orbital, and that makes it hyperreactive. Now, a little bit of this normally happens, and the body's ready for it. We've got this enzyme here, SOD, superoxide dismutase, and it will convert the superoxides into hydrogen peroxide, and then we can further neutralize them all the way down to water with these other enzymes like catalase or glutathione peroxidase, okay, and make them into water, and it's totally harmless, no big deal, okay? But you can run into problems if you've got a free iron around. So free iron can be a big problem in the human body, and we talked about how men tend to become iron overloaded in Western countries after the age of maturity, so after about 20 years of age, and women become iron overloaded typically in a Western country after menopause. Well, anyways, if you got free iron sitting around in the mitochondrial matrix, it can run a reaction with the hydrogen peroxide and convert it into these hydroxyl radicals, which are very damaging, and they can react with the inner mitochondrial membrane and cause a chain reaction of what's called lipid peroxidation. This is a form of oxidative stress. When the oxidants are higher than the antioxidants, then they can go around causing chain reactions that damage membranes, damage DNA, damage proteins. Okay, so Fenton reaction is easy to remember. Fe, ferrous for iron in Latin, and Fe for Fenton. So they both start with Fe. Okay, the other thing that can happen is if you have excessive nitric oxide. Nitric oxide is a gas, and it can diffuse around, and there are certain situations. I gave some recent lectures where I was talking all about this is called the no-oh-no pathway. So nitric oxide can interact with superoxides to form peroxynitrite, and this is bad. Okay, so this also can be very damaging to membranes, can also lead to formation of hydroxyl radicals. And this is when we start getting all the Martin Pall research. I gave a whole bunch of lectures on Martin Pall's research and on oxidative stress, but just be aware there are things that can do this. And so what you really want to do is not become iron overloaded. That's why I try to keep my serum ferritin. I want to get it below 80, like 25 to 80 would be perfect. Mine's probably about 120 right now. I was a little iron overloaded when I was younger because I didn't know any better. I used to eat the Raisin Bran cereal with the extra iron added because I thought iron would make me strong. You know, we had the image when we were young of Popeye that it's good to have more iron, you know, be big and strong. Eat meat like a big lions and tigers, okay, but it was stupid. And like I said, I got most of mine, I think, because I used to eat a box at a time of that Raisin Bran cereal, 2 a day. All right, so anyways, just be aware that this can go wrong. And when you have blockages of this electron transport chain in the intermitochondrial membrane, then you're going to get more electrons leaking off of coenzyme Q down onto oxygen here. You're going to form more and more of these superoxides. So you're going to get more and more of these chain reactions causing damage. You know, like when you have this random hyperreactive molecule in the mitochondria, it's like bouncing a super ball around. It just starts breaking things randomly. So you don't want that. It'll overwhelm the superoxide dismutase. So there'll be just too many of them too fast. Okay, and so yeah, when you talk about iron, the way to think of iron, and I think Eugene Weinberg is the one where I first heard this phrase. He says it's like a fire. You want a fire in your fireplace to keep you warm. You want a fire in your stove to cook your food. But you don't want fire anywhere else or it just damages things. That's like what iron is in the body. Iron is, because it's a transitional metal, it has a variable valence. So it's good for, like most commonly Fe2 plus, Fe3 plus, very good for handing off electrons in the active site of an enzyme. But you don't want it elsewhere or it'll start becoming autocatalytic and running reactions to make these free radicals that go around damaging things. Okay, there's a specific type of cell death related to excess free iron called ferroptosis. Okay, that's associated with lipid peroxidation. Okay, it's bad. All right, we're going to talk about iron more in an upcoming chapter. Okay, so this was just again sort of showing you these stages as the fat starts accumulating where it doesn't belong in the skeletal muscle, postprandial hyperglycemia, in the liver. Then you get fasting hyperglycemia because the liver especially regulates blood glucose during the fasting phase. Okay, so now here's where we see the most common problem. Excess dietary fat, especially saturated fat, but excess dietary fat in general will lead to what one can call overnutrition. Okay, and it'll tend to inhibit mitochondrial electron transport around here, around coenzyme Q and complex 3. And now you've got a problem because remember, everything is running like an assembly line, like a conveyor belt. And when you stop it, now everything backs up. So now you got a traffic jam backup of glycolysis, of Krebs cycle, then going into a backup of glycolysis, and you start leaking more electrons here, getting oxidative stress. Oxidative stress just means there's more oxidants than there are antioxidants. Okay, so if you keep on making oxidants, free radicals, ROS, reactive oxygen species, you're going to run out of the ability to handle them so well after a while. Okay, but this is the most important thing to know about inhibition. So McDougall said it fat paralyzes the insulin receptor, which is essentially the effect of it, but this is the step where things break down. Okay, and what are the things doing this, by the way? According to Michael Brownlee, I'll show you the Michael Brownlee paper a little bit later, but man, that guy's an incredible genius. He deserves a Nobel Prize. He deserves 2 Nobel Prizes for how he figured out diabetes and its effect on this intermitochondrial membrane, but he'll never get one because it's like what I've seen is who gets a Nobel Prize isn't so much how great their discovery is. It's more like if that Nobel Prize is going to help promote a lot of profitable things for a company, oh yeah, he'll get the Nobel Prize. But if that Nobel Prize is going to empower the public to eat a low-fat diet, oh, they don't want the public to know about it. So you'll never hear about it. I'm going to show you some of the greatest diabetes researchers in the history of the world, and nobody's ever heard of them. Okay. So again, here's what insulin resistance is all about. You normally have, after you eat a meal, there's a lot of glucose in the blood. And insulin is released then by the pancreas beta cells. It travels to the skeletal muscle cells and it'll bind the insulin receptor. And this is the plasma membrane, meaning the outer membrane of the cell of your skeletal muscle cells. And then the insulin receptor sends a signal to these vesicles that have glucose type 4 transporters in them. So that ends up being useful to know, glucose type 4 transporters. Okay, so then the vesicle will travel to the plasma membrane. It merges with the plasma membrane, and these glucose type 4 transporters then form a channel through which the glucose can come into the cell. So the glucose comes into the cell, then like we said in glycolysis, it'll get phosphorylated right here to trap it, so it won't be able to exit back out. And that's how you bring glucose into a skeletal muscle cell after you eat a meal. This is normal. This happens all the time, and most of your postprandial glucose that's floating around in the blood, the amount that's above normal blood glucose level, it's getting taken up by the skeletal muscle, and that's exactly what should happen. Skeletal muscle is the biggest organ in your body. Okay, so now here's what happens when you eat an excessive amount of dietary fat, and especially sat fat, but all the fats are going to contribute to insulin resistance. You get an excessive amount of electron carriers sent to the intermitochondrial membrane, and it starts pumping out too many protons into the intramembranous space, and the gradient goes too high. And once it goes above a certain threshold, you can't pump any more into it, and then electron transport starts to go backwards, and then you start leaking electrons into the matrix, forming superoxides, oxidative stress. The mitochondria actually recognize there's a problem. They recognize the chaos of the situation, and they send what is called an overnutrition signal. And they say, hey, we have got too much nutrition in this cell. We cannot take any more food stuff. Do not bring any more glucose into the cell. No glucose, no glucose, okay? It's much harder for the skeletal muscle cell to control how much fat gets into it. I'll explain that in just a moment. But they can shut down the entry of glucose. So I drew these arrows here of the glucose bouncing off the plasma membrane. Because the glucose type 4 transporters did not go up to the membrane because they got the overnutritional shutdown signal, this glucose will accumulate in the blood. And so this is after eating, so this is postprandial, meaning after eating, hyperglycemia, elevated blood glucose. Emia just means in the blood. All right, so now if this stays going on for a prolonged amount of time, this high glucose is going to then have a harmful effect on the cells that cannot regulate their amount of glucose uptake. And that includes, like we said, the eyes, diabetic retinopathy, the endothelial cells, diabetic microvasculopathy, the kidneys, diabetic nephropathy, some of the peripheral nerves, diabetic neuropathy. So it is a disaster. And usually in my experience, talking to these diabetic patients, they think that, and by the way, I got lots of lectures on diabetes. If you even just look at this YouTube channel, probably where the most value is you go to the playlist. And if you go to the playlist, you'll see tons of lectures on diabetes, lots of lectures on hypertension, lots of lectures on obesity, etc. But that's where you'll find, I think, the most value to really learn stuff. You'll find that the level of lectures I've got are way beyond anything in a medical school. Doctors really don't know much about diabetes. Now, I know you think I'm joking. I can actually tell you a story. I really wanted to understand diabetes better because I had looked at like 1,000 brains in a row, and I'm like, 95% of them, they're all diabetic. So, and hypertensive. At least 90% of them were diabetic. And I would say diabetic or hypertensive, 95%. Okay, but that little 5% gap, most of them had both. All right, so I wanted to really understand diabetes. I read all the regular books. I read the textbooks. I read a bunch of papers. And I asked, I talked to some nurses and doctors. Who are the best, diabetes experts? And I went and I met with these diabetes experts, okay? None of them had read any of the papers. I asked them, what do you think of the Sweeney paper? What do you think of the Hemsworth paper? What do you think of the Rabinowitz paper? What do you think of the, the Brownlee paper? What do you think of the Shellman paper? What do you think of the Taylor paper? What do you think of Nathan Pritikin? What do you think of Walter Kempner? They didn't know any of them, not a single one of them. And these were the doctors that trained the fellowship trainees in endocrinology. They don't know it. It's amazing. It's amazing how ignorant doctors are about the causes of disease. And the reason is pretty simple. We talked about this before. If a doctor knew the cause of a disease was dietary, then the treatment would be diet. By them being ignorant of the fact that there's a dietary cause, then they're only trained to prescribe a drug, and that makes money. So that's the way the medical schools are. It's not the doctors don't even know. I wasn't even aware that all this nutrition, toxicology, epidemiology stuff existed, and I was a great student. So it's just not taught to them. It's the way they're kept ignorant so that they, become drug dealers instead of healers, unfortunately. And they want to help the patient. They just don't know what to do. And then by the time they're done with their residency, they're so exhausted from working such long hours. Being a doctor is a little bit like being a highly educated assembly line worker. It's go, 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 go. So most of them lose interest in reading. I know lots of doctors, very few read anything medical or nutritional or anything. There's some who do, but they're the rare exceptions, not common. Okay, so anyways, now we're going to talk about a major problem with diabetes. Okay, this is a really good paper. I think the author's name was Anthony J. I think the other author was maybe Hamilton or something. And here's the point. They wanted to try to understand better how was the fat getting into the skeletal muscle cell. And so they inhibited the fatty acid transporter. CD36 is a fatty acid transporter. Sometimes it's even abbreviated FAT, fatty acid transporter. Okay, so anyways, what they found was no matter how much they inhibited the fatty acid transporters, the fat just kept coming into the skeletal muscle cell. And it appears that the mechanism by which the fat was getting into the cell was it'll become protonated here so that it's no longer charged, and it'll insert itself into the outer leaflet of the plasma membrane, and then it's able to flip into the inner leaflet of the plasma membrane, and from there move into the cytoplasm. Okay, so this is actually called the flip-flop maneuver of fatty acid entry into skeletal muscle. And the drug inhibitors didn't make that significant a difference. The only thing that would change it is how much glucose was in the blood. This research with live cells. Okay, so that's pretty interesting. Okay, we're going to stop here. And this will be the end of, I'm calling it Chapter 8A, and then later on I'll start with Chapter 8B. Oh, and then a lot of people, these keto, paleo, carnivore, low-carb people try to tell you, oh, there's high meat-eating populations that are healthy. What about the Maasai in Africa? Well, the Maasai in Africa, they do have big diameter arteries because they exercise like crazy, traveling around with their cattle, but they also have a tremendously large amount of atherosclerosis, and that's been shown by autopsy studies on them. And they don't live that long. Okay, the next thing is the Eskimos. The Eskimos have very poor health. Tons of osteoporosis, atherosclerosis, and Dr. McDougall actually made pretty nice videos about both of them. So anyways, that's where we're going to end it for today, because the next thing we're going to go into a little bit more advanced metabolism with diabetes. So hope that was interesting.